Okay, gang. Welcome, everybody. Today's background, as long as it lasts, is Picard's Ready Room. So that's my background for today. Any questions before we get started? Any questions before we get started?
I have one concern that I just found out when logging into Moodle. Could you please possibly reset the dates for the course because it's not showing up under my courses anymore?
That sounds pretty weird. Send me an email about that. I don't know why it wouldn't be showing up under your courses.
It's not doing mine either.
Really?
Yeah.
Okay. So I've gone into Moodle and I edited it by removing the weekly summaries, but those don't mean anything.
I think there may be an algorithm or something that when you have those dates set, it will show that on your main course tab. If you click the 2020 tab, you can see the CSC 475 there. So I think maybe those dated sections might have some automated system where it refreshes based on whether it's in the current week or not.
Okay, yeah, so the course is still there. Everybody should still be able to get to it because I've done that many, many times in the past. I don't like all those weekly summaries. I like to have things, you know, like lectures, resources, exams. So I renamed some of them and then I just delete the rest of them. So if you can't find, they should still be there. If they can't find them, talk to somebody else in the class. And if you still are stuck, talk to me. I see a lot of people saying, yeah, they're still there. You just have to search for them a little bit. I'm sorry for that hassle. I guess in the future, I'll try to remember to leave the last date there. Maybe I'll just hide it. Maybe that'll help it. But anyway, on Moodle, you should have today's notes, or at least a rough draft of today's notes. And if you check the audiovisual assets section, all of the videos that I'm going to talk about today should be in there. Another thing too, while I haven't explicitly said it, everything that, most everything, I'm not going to say everything, most everything that I've been covering is in the last two chapters of the Science of Computing and Introduction, the textbook that I wrote for CSC 100. And if you go and you click on the link that's there under the online textbooks, it'll take you to that textbook. And the second to last chapter is artificial intelligence. Most of the videos that I've been going over are actually embedded in that HTML version of the textbook, so they're in line. So you can basically read about a subject, and then instead of having just like a picture like you would in a regular book, there's generally an embedded video there. So what I'm showing here is are actually some of those videos that are in the textbook. So that might be a little bit easier centralized location for you to get to them if you want to. It's just up to you. I've tried posting them, like I said, under the audio video assets of Moodle as well. I see we're down to 32 people today. There's supposed to be about 40 of you here. I may have to start taking roll or giving pop quizzes or something if more people don't start showing up. Of course, the videos there are recorded, but it's a lot better if you watch them live so you can ask questions, etc. Okay, so today we're going to pick up from where we left off. Last time we were talking about the history of artificial intelligence, and to recap a little bit, we started at the birth of AI, which the term artificial intelligence was coined in 1956 at the Dartmouth Conference, and so that's really what most people mark as the start of artificial intelligence research, even though we've talked about it goes back further than that. Alan Turing's paper that laid out the Turing test was in 1950. So even in the 1940s and 50s, people were talking about aspects of AI. There just wasn't a name for it yet. But 56 is generally given as the birth date of artificial intelligence. And then after the birth of it, there was the early optimism that lasted really for the first decade and a half of artificial intelligence research. There were a lot of early successes, which we talked about last time. Programs that could make an A on the MIT calculus exam for freshmen, that sort of thing. People got really excited. But as the 60s drew to a close and we began to get to the 1970s, all of that early optimism turned to pessimism because there were just lots of problems that there was like almost no progress made on. Vision, for example. Automated translation is another example. Those were problems that just didn't seem to fall. And the problems that we did make progress on, we came up against the brick wall of exponential growth and complexity, which meant that we could only really work on tiny problems, on small problems. So the 1970s was really a bad time for AI. In fact, there are stories about professors begging their bright students not to go into artificial intelligence research because they considered it such a black hole, basically a dead end. But that was the 70s. By the 1980s, what was happening there, as we talked about, that was the era of expert systems, which were these small programs that acted like a human expert in a very narrow problem domain. These systems were kind of, people sort of decided that the core AI problems, building an artificial general intelligence, was just out of reach completely. And so they asked themselves, well, what can we do with the stuff that we know works? And that led to expert systems, which were relatively small programs that acted like a human expert in a narrow problem domain, like I said, infectious disease diagnosis, for example, or maybe oncology, cancer, and really a particular type of cancer, maybe. So the expert systems were the first really commercially successful products of AI research. And that was really the focus in the 80s and early 90s was, okay, we can't solve what we set out to solve. We can't build an artificial general intelligence, but at least we can do something that has economic value in it. So that was the 1980s. And these dates are all, please don't say, oh, in 1970 this started and in 1980 it ended. I'm giving you kind of a general feel or a general overview for what was going on in a particular time span. They're not hard and fast dates on these things, but in general, I've explained what was happening in the 60s, what was happening in the 70s, what was happening in the 80s. Well, the 1990s were what I would call incrementalism. And basically, incrementalism, there was very little apparent forward progress towards the greater goals of AI, building an artificial general intelligence, for example. But there were seeds of progress that were starting in the 1990s. And again, these dates are approximate. I can remember when I was getting close to graduation at University of Louisiana, Lafayette, there was a talk, a guest lecturer who came to talk about machine learning. And I don't remember who the speaker was. That's unfortunate. It might have been somebody famous. But the talk was about progress in multi-layer neural networks. And I think specifically they were talking about the backpropagation algorithm, which we're going to cover in this class. And, you know, it was a talk about how, you know, these learning machines showed a lot of progress. Well, it was very, very funny because normally you had to like beg graduate students to attend talks that were being given on, you know, technical talks that were being given in the computer science program. Excuse me, my voice is going out. So this particular talk, they had scheduled for a classroom. It was a larger classroom, but it wasn't like a lecture auditorium or anything like that. And the funny thing was is that the graduate students, the audience was standing room only. I'd never seen a talk like that. Every desk was filled. Then there were students standing along the sides of the wall and in the back of the classroom. And so the guy gave the speech, and the old professors, you know, who get to sit on the front row, you know, sat there quietly. They didn't say very much. Maybe they asked a polite question or two, and they were ready to leave. But after the talk, the speaker was like inundated with graduate students coming up and asking all sorts of questions. And that's generally, if you stay around academia a while, that's generally a good sign that something's cooking. when all of the young people are super excited about something and have, you know, tons of questions, and the old guard is kind of seen it, done it, there's nothing to this, move along now. That's usually a sign that something's cooking. So, you know, in the 1990s, you know, there was starting to be, you know, a lot of interest, you know, by young computer scientists and some of the old guard who'd been working on these problems for a long time. Geoffrey Hinton, for example, I mean, he never gave up. He kept working on it all the way through. And he's now in his 70s, maybe, could be 80s, but he was kind of the father of backpropagation. He works at a university in Canada, and it's funny because for most of his career, again, you know, he was kind of considered this crazy guy working on this idea that's never worked out. But, you know, since neural networks has changed the world in the last decade, it's kind of funny. Google now gives the guy a big hunk of money every year. They don't have to, right? Because everything that he did is public domain and published. But they throw a huge chunk of change his way and basically just say, you know, thank you for everything you did, and just, you know, keep playing on these ideas. Maybe you'll come up with something brilliant again. So I think that's really, it's kind of Google. They don't have to do that, but it actually, you know, is a wonderful show of respect that they're kind of taking care of one of the very few professors who kept pushing neural network research when everybody else had pretty much, you know, thrown it on the dustbin of history. So anyway, he was doing a lot of work in the 90s and early 2000s, working on ways of getting multi-layer networks to learn. But again, in the mainstream, you know, there wasn't a ton of funding for AI research. Again, expert systems were becoming, you know, were still the big thing. They were actually making money, but that's pretty much the way things were in the 90s. In my AI class, I devoted a lecture to machine learning, which is way more than most profs did. for that subject. Most of them just ignored it through the 1990s because everybody thought there was nothing there. But in the last decade or so, say 2010 to 2020, but really maybe you could go back as far as 2005. But in the last 10 years, maybe 15 years, the internet has really come into its own. Big data has come into its own, and machine learning has come into its own. And those three things together, the internet, which basically provided connectivity for lots and lots of computing power, and also tons and tons of data. Everything is online now, almost everything. And the science of big data is like, well, how do you make sense of all of this free-form textual data that's out there? That and neural networks based on multi-level neural networks that use algorithms like backpropagation have really enabled this explosion that's taken place in the last decade or so. So right now, there's a huge amount of forward momentum in AI. There are articles that come out, every few months, sometimes every few weeks, touting the latest breakthrough. There has been tremendous progress on problems like vision, speech recognition, machine translation, deep learning, self-driving vehicles, et cetera, et cetera, et cetera. And people are excited about and concerned about the development of artificial general intelligence. And so that's really been the last decade or so. So that's kind of the history of AI from its beginning to where it is today. Next, what we're going to do is we're going to look at 4 specific areas in a little bit more depth. We've talked about each of these at some level already, but I wanted to talk a little more about machine learning as it applies to machine translation, because that's such an important topic, machine translation. And by machine translation, I mean software, hardware systems that can translate from one human language to another human language. So say from English to Spanish, or from French to Italian, or German to English, or whatever. After we talk about machine translation, I apologize, man. My voice is just having a hard time today. I'm very sorry about that. But after we talk about machine translation, we're then going to talk about natural language understanding, which we've talked a little bit about earlier. And again, the difference is machine translation is from one human language to another human language, where natural language understanding is trying to get a computer to understand what a human is talking about. The next thing that we're going to look at is computer vision, and then we're going to end up with autonomous vehicles, sort of self-driving cars and things like that. So we're going to talk about these 4 areas today. And again, like I said, we've already touched on some of this stuff. I'd like to start with showing a little video from the early days where people were all excited about machine translation and what was possible. So you can see, what people thought that it would take. So you can see what people thought that it was going to take to be able to do machine translation in the early days, and they really thought it was going to be a simple problem, not a really complicated one. So let's see. Let's see if I can share my screen.
They hadn't reckoned with ambiguity when they set out to use computers to translate languages.
A $500,000 supercalculator, the most versatile electronic brain known, translates Russian into English. Instead of mathematical wizardry, a sentence in Russian is to be said in
One of the first non-numerical applications of computers, it was hyped as the solution to the Cold War obsession of keeping tabs on what the Russians were doing. Claims were made that the computer would replace most human translators.
At present, of course, you're just in the experimental stage. When you go in for full-scale production, what will the capacity be? We should be able to do about, with a modern commercial computer, about 1 to 2 million words an hour. And this will be quite an adequate speed to cope with the whole output of the Soviet Union in just a few hours computer time a week.
When do you hope to be able to achieve this speed?
If our experiments go well, then perhaps within 5 years or so.
And finally, Mr. McDaniel, does this mean the end of human translators?
So yes, for translators of scientific and technical material, but as regards poetry and novels, no, I don't think we'll ever replace the translators of that type of material.
Mr. McDaniel, thank you very much. But despite the hype, it ran into deep trouble. This straightforward Russian passage poses no trouble for a human translator.
С успехом применяется аппарат булевской алгебры. In the present paper, we propose using matrix Boolean algebra, and we describe some results which we have already obtained in this way.
But when it was given to a computer, this was all it could come up with. Present general particle writing clause, to be offered to be proposed, we suggest, for investigation, research, analysis, exploration, paper essay, such a sort of short-time family chat standards, utilize to take advantage of matrix Boolean algebra and n to be described row series. Result gotten in a 224 on n. This direction trend on.
So you can see there that in the early days, what they were trying to do is they were trying to use the tools of linguists, right? Where you have vocabulary and you have sentence structure and you have the parts of speech. You have nouns, you have verbs, you have adverbs, you have adjectives, and they thought that you could just use these rules, right, to map Russian into English or vice versa. I mean, what do you need? All you need is a dictionary, right? It says this word in English, means this word in English means this in Russian, and vice versa. How hard can it be? Well, it's a lot harder than that. I mean, you can get something where you translate every word verbatim in a sentence, and what you get out is basically the kind of gibberish that they showed there. Because words can have lots of different meanings. One example that I like to give, it's a humorous example, but it makes a point. And I usually talk about this in my theory of computing class when we're talking about syntax and we're talking about ambiguity, is I love the sentence, time flies like an arrow. If I say that to you, you know what that means. It means that time passes quickly. Now, I didn't say that time passes quickly, right? I used an analogy, right? Time flies like an arrow. Well, time doesn't literally fly like a bird with wings. But if you say that something flies, it speeds by quickly. And if you compare something to an arrow, it's the same thing. An arrow whishes very, very quickly. So if I say time flies like an arrow, I mean, even though I didn't say that time goes by quickly. So that's an example of a sentence that doesn't say actually in words what it means. So that's a big problem. The other problem is that if you don't know what time is and you don't know what arrows are and you don't know what it means for something to fly and you don't understand that allegorically time can speed by, so saying that time flies makes sense, you could come up with some really weird meanings for that sentence. So, for example, there are time machines, right? If you don't believe me, read the novel, right? The Time Machine by H.G. Wells, right? So if I say a time machine, everybody knows what I mean. So time is not only a noun, right? Time, it can also be an adjective, time machine. So why can't you have time flies? I mean, flies are things. There are lots of different, there are house flies. Why can't there be time flies, right? So these particular time flies, they like an arrow. They're really in love with this particular arrow. So if you don't know that that's completely nonsensical, if you're just going by dictionary words and the parts of speech, that's a valid translation of that sentence. There's a particular kind of fly, a time fly, and it likes an arrow. But time can also be a verb. I'm timing how long this lecture is taking. So you might have a sentence. That sentence might mean you. I want you to time. What do I want you to time? I want you to time flies. How am I supposed to time flies? Like you would an arrow. Time flies. Time flies. I want you to time flies like an arrow. So there are all these ridiculous meanings, but why are they ridiculous? Well, because you know you would never time flies like an arrow. That doesn't make any sense. You can't time something like an arrow, and there are no, it doesn't make sense to time flies, right? So you don't even consider those other meanings because they're nonsensical based on common sense. Well, but how is the computer supposed to get that common sense so it knows what things are reasonable and what things aren't? And so the problem is complex. While on its surface, people thought, oh, we need the dictionary and the parts of speech, and we can put this together, and it'll work out great. It didn't work out great at all. It was terrible. So, what's the modern day approach? Well, the modern day approach, as I talked about, as I mentioned a couple of lectures ago, is to use a statistical approach where you compare known texts that are written in both of the languages. And so if I know that this text and this text say the same thing, I can look for statistically significant correlations between phrases in one and phrases in the other that must mean the same thing, because these documents, a human has told me these documents mean the same thing. So if you're given millions of documents that humans have translated into multiple languages, then it's like you've got Rosetta Stones for these languages and enough computing power to match to come up with the statistics will allow you to do a pretty good machine translation. So let me see if I can't find this one.
Google Translate is a free tool that...
Hold on a second. By the way, are you guys hearing these things okay when I hold the phone up to the speaker, or is it still quite low?
You're pretty okay.
All righty, that's good to know. Let's see. I think this is the right one.
Google Translate is a free tool that enables you to translate sentences, documents, and even whole websites instantly. But how exactly does it work? While it may seem like we have a room full of bilingual elves working for us, in fact, all of our translations come from computers. These computers use a process called statistical machine translation, which is just a fancy way to say that our computers generate translations based on patterns found in large amounts of text. But let's take a step back. If you want to teach someone a new language, you might start by teaching them vocabulary words and grammatical rules that explain how to construct sentences. A computer can learn a foreign language the same way, by referring to
So
vocabulary.
this is the first approach we were talking about.
But languages are complicated, and as any language learner can tell you, there are exceptions to almost any rule. When you try to capture all of these exceptions, and exceptions to the exception, in a computer program, the translation quality begins to break down. Google Translate takes a different approach. Instead of trying to teach our computers all the rules of a language, we let our computers discover the rules for themselves. They do this by analyzing millions and millions of documents that have already been translated by human translators. These translated texts come from books, organizations like the UN, and websites from all around the world. Our computers scan these texts looking for statistically significant patterns. That is to say, patterns between the translation and the original text that are unlikely to occur by chance. Once the computer finds a pattern, it can use this pattern to translate similar text in the future. When you repeat this process billions of times, you end up with billions of patterns in one very smart computer program. For some languages, however, we have fewer translated documents available, and therefore fewer patterns that our software has detected. This is why our translation quality will vary by language and language pair. We know our translations aren't always perfect, but by constantly providing new translated text, we can make our computers smarter and our translations better. The next time you translate a sentence or web page with Google Translate, think about those millions of documents and billions of patterns that ultimately led to your translation. All of it happening in the blink of an eye. Pretty cool, isn't it? Give it a try at translate.google.com.
So again, there's absolutely no understanding of what's going on there. The computer has no idea, you know, what it's translating. It's just doing string substitutions. That's truly all it's doing, is substituting one string, say an English string, for a German string, where those two strings match up because they've appeared in multiple documents at the same place. So with enough of those examples, you can begin to get a reasonable translation quality. Now, up until recently, these things have run offline. In other words, not in real time. The non-real time ones have gotten really good. I mean, if you look, almost all YouTube videos, if you click the closed caption button, it will generate at the bottom of the screen closed captioning for what's being said in the video. A human didn't do that translation. It comes from an algorithm, and most of the time they're pretty good. I do find it funny sometimes to listen to technical videos, and when there's a video on a very technical subject, it tends to use words. We tend to use words in those videos that are not very common words. And because of that, it's funny because sometimes the closed captioning system will begin to break down and give you words, English words that sound kind of similar to what's being said but make no sense in that particular instance. But you can see why it happens, because if the systems don't have very many examples of those things, then they're more prone to error. So that's why a technical thing may not be translated as good as something that's a little less technical. But one of the things that's been happening recently is real-time translation. Let's see if we can look at that. Let's see. Guess I didn't resave it. Oh, yeah, I did, but it's in a different tab. Let's see. So this is called interpreter mode for Google Translate. Oops. So this is called interpreter mode, and this allows, it's the beginning of allowing real-time conversations for people who speak different languages.
Hi there. How can I help you?
Hola, ¿habla español?
Sorry, I only speak English, but you can select the language you speak.
Español.
Hey Google, be my interpreter.
What language should I interpret to?
Spanish.
Okay, go ahead.
How can I help you?
¿Cómo puedo ayudarte?
Estoy buscando un lugar para almorzar antes de ir al aeropuerto.
I'm looking for a place to have lunch before going to the airport.
What would you like?
¿Qué te gustaría?
Quizás una pizza o una ensalada.
Pizza or salad?
There's a great place around the corner. You can take the train from there to the airport.
Hay un buen lugar a la vuelta de la esquina. Puedes tomar el tren desde allí hasta el aeropuerto.
Perfecto. Gracias.
Perfect. Thank you.
No problem. I hope you enjoyed your stay.
Esperamos que hayas disfrutado tu estadía.
And I don't know if you noticed or not, but my own Google decided that it wanted me to start translating. So I don't know if you heard that in the background, but oh yeah, I see all of the rest of you are going, oh yeah, your Google assistants went off. Sorry about that. But it is pretty funny. All you people with your microphones in your house, of course, dude, join the 21st century. Get your Google Assistant. The government already knows everything about you, man. So just give in and live a little. Gosh, I mean, I think I may have already mentioned this. I've got like 5 of them in my house. I got one in my master bath. I've got one in my master bedroom. I've got one in my kitchen. I've got one in my den. I got one in my guest bath. I put them in my guest bedrooms, but the people who've stayed with me have asked me not to do that. So I guess they're a little less trusting than I am. Anyway, so that that's a fairly new video that I played. So that's pretty much the state of the art of what that kind of translation's like these days. It's still a little clunky. I don't know if I would use it if I were traveling. The last time I was out of the country was 3 years ago, and there were already some pretty crude versions of it, but I never tried when I was like in France or Italy to use it. Although a slightly different app is one where you use your camera and you point it at text in one language and it translates to another. I found that quite useful in the Louvre when I was in France. To read the descriptions of some of the art objects. So I did use it there quite a bit. That was actually quite nice to have because some of the descriptions they were kind enough to have in both French and in English, but some of the descriptions were only in French, and so it was kind of nice to be able to let your phone look at the text and translate it for you into English, so you could know why you were supposed to be impressed about this particular object of art. So, but anyway, so that's where translation is at these days. But I keep saying this over and over, and I keep repeating it because it's so important. Google Translate and these kind of applications have no understanding of what the words and the sentences they are translating actually mean. They don't know what they're translating. They just know that one string in English matches to this other string in Spanish, or this utterance in English matches to this utterance in Spanish. That's all they know. So they're just doing string substitution. That's all that's happening there is string substitution. So let's look at next. So we said our first thing we were going to look at is machine translation. We said the next thing we were going to look at was natural language understanding. Or you might say what we're doing here is looking at, using language intelligently. One second. Sorry about that coughing fit. Hopefully I'll be better now. So, as I said, natural language understanding. Now, we've already talked about this one in a little bit of detail. Essentially, in natural language understanding, if you want to have a conversation with the computer, there are three phases to it. Kind of made fun of the middle phase last time we talked about this. There's automated speech recognition, which is converting spoken speech, human speech, into text. That's the first step. And then there has to be some kind of an understanding step. And then the last step is taking the output text and converting it via text-to-speech back into a spoken answer. And the first two pieces of this, the first piece and the last piece, we pretty much are solved now, are pretty much solved problems. But it hasn't always been that case. And really, automated speech recognition has really only become a solved problem in the last 10 or 12 years. Before that, it was considered one of the unsolvable problems. For many years, for decades, in fact, automated speech recognition, there were three factors that were always considered. One was the vocabulary size. So it was fairly easy to build a small vocabulary system and much harder to build a large vocabulary system. And, the reason for that should be obvious. If we have a system and we only need two words, yes and no, yes and no, that's very, very easy to get because there's only two possibilities, and the sound and the sound are very different. You could actually build, and back in the 1930s they did, a completely analog system that would look at whether you were getting a sound or an O sound, and just with analog components, you didn't even need a computer. You could build a machine that could tell the difference between yes and no. And in fact, the 1939 World's Fair, General Motors had a pavilion where they had, I need a video on this because it's actually very cool. They had this big giant robot. He was something, the Moto Man, and you could speak to him. Of course, there was a presenter who spoke to him, but he could recognize yes and no, which is extremely impressive. So if you make a vocabulary that's tiny enough, just two words, well then it's a very, very easy problem. If you make a vocabulary that's larger, say the digits 0 through 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, well, now you've got a problem that's, 10 times harder because there are 10 things to recognize. That'd be 5 times harder because the difference between 2 and 10. One of the ways that they limited automated speech recognition systems for decades was to make them small, the vocabulary being small. But even then, they weren't very good. I remember in the, I was already a professor, so I will say in the late 1990s, my brother-in-law was a insurance adjusters for General Motors Corporation, and by the late 90s, late 90s, I don't think it was the 2000s yet, they started to reduce costs and stuff like this. They tended to have their insurance adjusters start working from home and using automated productivity tools. And one of the productivity tools that they had was a system where you would had to say case numbers, right? Rather than key them in, you would say them. And my poor brother-in-law, he became so frustrated with the system that he did a very natural human thing, but completely the wrong thing. And that is, whenever the system would misunderstand what he was saying, he would do what you would do for a human who was having trouble understanding you. You would raise your voice, right? So I can remember one day I was visiting them, and I was in the kitchen with my sister, and my brother-in-law was back in the back bedroom that he had converted into an office, and I hear him shouting, 0, 0, 2, excuse me, just shouting at the top of his lungs. And I'm like, sis, what in the world is Charles doing? And she's like, oh, well, he has problems with that newfangled computer system they have him using. And I'm like, sis, look, when I'm not around, take Charles off to the side and tell him it's not having problems hearing him, it's having problems understanding him. And the more he shouts, the more stress he puts in his voice, and the worse the recognition is going to be. He'll have much better results if he just talks calmly in a voice, pauses between each word, and doesn't raise his voice even when it gets the numbers wrong. So, but it was hilarious to me as a computer scientist who studied AI, and I knew exactly what was going on. But you think about it from a human's point of view. If you've got a human who can't hear you well, what do? You raise your voice. And of course, that was exactly the wrong thing to do. So, that was 20 years ago, maybe a little bit more. So small vocabulary size. The other thing was speaker dependent versus speaker independent. A lot of systems required that you train them on your own voice. So Dragon was a big, Dragon Systems was a very big software company, very, very popular in machine translation. Actually, Raymond Kurzweil did Kurzweil Naturally Speaking. He created a company that did voice to text, automated speech recognition. And he eventually sold it, but that name pops up in a lot of places. So that was one of the things Kurzweil did. But generally in those systems, what you had to do is you would have to read a few pages of material to the system so that it could build a model of your voice. And you might say, well, that would be a pain in the It was, but But a lot of times they were popular in legal offices and doctors' offices where there's a very sort of specific vocabulary, and it was worth the time to train the system so the doctor could just speak his notes and have them translated. Those systems are still used. Last year, a little more than a year ago now, I hurt my shoulder, and I needed 6 months of vocational rehabilitation. Basically, I'd go to Green Clinic 3 times a week, and I would exercise. And so they have a little gym in Green Clinic where you exercise. They give you exercises to do, and then they stretch your arm and stuff like that because it was a shoulder problem. But I would notice that the physical therapists they would record their observations with a piece of software that would translate them into text. So those kind of applications have been popular in medical settings for several decades. But that was the deal. Speaker dependent, which means you had to train it, versus speaker independent, meaning that anybody could talk to it. Now, the trade-off was that you could generally get better recognition in a speaker-dependent system, and you could generally deal with a larger vocabulary if it was speaker-dependent. But you had to go through the training, and only you could use it, right? You had to use your voice profile. The last big factor, there were 3 factors, like I mentioned, that were important in automated speech recognition, was continuous versus discrete utterance. When you listen to me now, you are hearing continuous speech. You are hearing continuous speech. If I put pauses between each word, it is very hard to speak this way for any length of time, but doing that, separating the words, made it much easier. So some systems required discrete utterances like that. For example, the digit program that I was talking about my brother-in-law using, you had to pause between each digit. So you couldn't say 1, 2, 3, 4, 5, 6, 7, 8, 9. You had to say 1, 2, 3, and pause. And by doing that, the computer would know you were giving it a big hint as to where the words began or ended. You know, if you say a phrase, my French is so bad I'm not going to even try, but if you say a phrase in a language, if someone says a phrase in a language that you don't speak, it just sounds like a stream of words. But when I speak English, you automatically hear the individual words, even though I'm not saying the individual words. I'm saying one long stream, one long stream of sound, but your brain picks out the individual words in it automatically, so I don't have to stop between each word. But getting a computer to do that, that was really hard. So for many, many decades, the rule was there are 3 factors with automated speech recognition: vocabulary size, which could be large or small; the speaker, is it speaker dependent, i.e. trained, or is it speaker independent, as in anybody can speak to it; and is it continuous versus discrete utterance. Obviously, what you wanted was a large vocabulary, speaker independent, continuous utterance recognizer. But for many decades, it was, these are 3 things, you get to have 2 of them. So you could have a large vocabulary size and speaker independence, but then you had to pause between the words. Or you could have, if you have a smaller vocabulary size, well then maybe that could be continuous and speaker independent. So that was generally the rule. Here are 3 things you want, you get 2 of them. And it was that way for decades. But everything changed in 2008 when Google, it's always Google, isn't it? When Google came out with its first when Google came out with their first large vocabulary, speaker independent, continuous utterance recognizer, and that was a big, 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 big deal at the time. So what I'm going to do is I'm going to show you a video from 2008, from November of 2008, so right towards the end of 2008, that introduces Google's voice search. I think I'm only playing the first 30 seconds or so of this.
Thanks for checking out Google Mobile app. Let me show you what this app can do. Pictures of the Golden Gate Bridge at sunset. Cool, right? Google search results just by talking into your phone. After you start Google mobile app, just lift the iPhone to your ear, wait for the beep, and speak. How big is the giant squid? Google mobile app uses the phone's motion to know when to start recording. And when you're done speaking, it automatically does a Google search. See?
Now, you might look at that and you might say, well, that looks pretty much like what we have today. What's the big progress since 2008? Huge progress since 2008. All that was doing was automated speech. All that was, I can say that now. At the time, I mean, when I would show it in class, everybody would go, ooh, this is so great. But all it's doing was automated speech recognition. So it would take what the person said, it would behind the scenes translate it into text, and it would just feed that text into the Google search engine. It didn't, notice all it did was present you with Google search results. It didn't try to synthesize that into an answer and use voice to give you that answer. So it was tremendously impressive for its time. No one had ever had a large vocabulary, speaker-independent, continuous utterance recognition system, and that was fantastic. And so, you know, it was earth-shattering, but it still was extremely limited compared to what we were doing, what we can do today. In other words, it wasn't really doing natural language understanding. It was doing automated speech recognition with a large vocabulary, speaker-independent, continuous utterance. So it broke the 2 out of 3 barrier. But it wasn't trying to construct an answer, as it were. So how do things tend to work now? Well, if you think about Google Assistant or Alexa, or to a lesser degree Siri or Cortana, how do they answer questions? Well, there are really 4 different. I'm showing the 3 fingers. 4. I can count. I promise. At least 4. There are basically 4 steps. The first step is automated speech recognition is used to convert a spoken question into text. And then the second thing that's done is a search is generally performed on that text to generate some search results. But then those search results are fed into something called a knowledge graph that's used to construct an answer to a question. And then the last step is text-to-speech technology is used to speak the answer. Now that third step, the knowledge graph, is not really machine learning. It tends to be good old-fashioned AI, what we would call a slot and filler approach, where it's got some sort of a framework and it's filling in pieces of information, and from that it can answer other questions. This enables us to have the very again, I am sorry for all the coughing. Maybe because it's so rainy today, I don't know. It allows you to have some very, very simple conversations, but only very, very simple conversations, because there's not much of a model that Google has. Now, you can, I did the whole thing last time about, the Prime Minister of Canada and his family and all of that. It's not like that's the only example. Okay, Google, what's the weather like today?
Today in Ruston, it'll be raining with a forecasted high of 68 and a low of 64. Currently, it's 66 degrees and cloudy.
What about tomorrow?
It'll be rainy there tomorrow with a high of 68 and a low of 62.
So you can, thank you. So you can see that, that you can ask follow-up questions about, say, the weather, for example, because it kind of, once it knows, oh, the topic of conversation is weather, people are going to ask about the high, they're going to ask about the low, they're going to ask if it's going to rain, they're going to, you know, so you can anticipate the kinds of knowledge you need. And if I say, what about tomorrow? And it knows that my last question was, you know, about the weather, it knows that I'm asking about tomorrow's weather. Now, that's gotten really good over the last couple of years. When they first introduced it, it wasn't so great because a lot of times Google would, quote, forget about the subject. And I never read an article, but I think what was happening is obviously there's only so much memory. And what I assume would happen is, because they're processing, you know, questions from hundreds of thousands of people continuously, and I assume that if the query volume was too high, that they would just flush out the memory. But if the query volume was lower, then it could hold the conversation frame in memory longer. When I first, probably 3 years ago, started doing the President of the United States family or the Prime Minister of England, you know, his family, sometimes that would die about halfway through. And I think it was because the knowledge graph about my questions ended up getting flushed. That doesn't happen very much anymore. Obviously, the systems have grown in capability. So that's kind of what's going on there. Now, if you keep the topic of conversation very narrow, you can come up with some really good applications. And this next one that I want to show, it made a big splash a couple of years ago. I'd say probably 2 years ago this came out, and it was all the rage. Let's see if I can bring this one up. Let's see.
How may I hear you?
Hi, I'd like to reserve a table for Wednesday the 7th.
For 7 people?
It's for 4 people.
4 people when?
Next Wednesday at 6 p.m.
Oh, actually, we leave there for like after like 5 people. 4 people, you can come.
How long is the wait usually to be seated?
When, tomorrow or weekday or?
For next Wednesday, the 7th.
Oh no, it's not too busy. You can come for 4 people, okay?
Oh, I gotcha. Thanks.
Now, that is incredibly impressive. And yeah, I see some people say, Google Duplex.
लेटेस्ट टेक्नोलॉजी गैजेट्स और ऐप्स के लिए सब्सक्राइब कीजिए अनबॉक्स टेक लाइव को और प्रेस कीजिए बेल आइकन को ताकि आप हमारे हर नए वीडियो के बारे में जान सकें।
I think somebody needs to mute. Or do I have a video still playing in the background? That's me. I've got a video playing in the background. Sorry about that, guys. So yeah, like I was saying, that is extremely impressive. And it's in Google Assistant now. It's been moved from Duplex into Google Assistant. So some people are saying, I wish Google Assistant could do that. I think it can. It may not be here poll. I see some people saying, I wish that would come to Ruston. You guys might check. I did not check before today's lecture to see if it's actually available here on my Google Assistant. I do know that it is available in some places. It caused a huge amount of controversy when it first came out because some people were saying that it was too good, that the inflections that it did, the ums and the ahs and things like that, were too convincing. And so I think they added a little bit after that, so that at the start of a telephone conversation, it says, I'm Google Assistant calling for, I'm Google Assistant calling to make reservations or something like that. But remember when I said that text-to-speech was getting to the point where it's close, if not indistinguishable from a human? I would dare you to identify that was a computer speaking and not a human. So, but again, that's a very limited environment. So it's limited in what the computer needs to say. It's limited in the types of it's limited in the types of things that a human is likely to say. It's limited in the types of things that that the computer is going to need to say. One of the things that I found fascinating about it is, if you notice in that one how fault tolerant it was. The human was having a very hard time understanding the perfect English of the system, but the system just kept right on going, right? It had initially asked for a reservation at 7 p.m., but the person on the phone heard 7 and thought 7 people, right? And once the computer said, no, it's for 4 people, and then it was like, well, what day? And I mean, it had already said, for Wednesday, for 7 p.m. But it did a very good job of seamlessly handling that conversation. Probably a better job than I would have done if faced with someone whose English was so poor, quite frankly. But it's very impressive. That sort of thing excites me and excites a lot of people who are into AI research. It worries some people. It scares them because they look at it and then they start thinking of all the evil ways that technology could be used. And yeah, there are evil ways that technology can be used. When you get a spam call these days, how do you know it's really a person, and not just a computer system. Anyway, it's fascinating. The technology is only going to get better. I look forward to the day where my assistant, can field, conversations from your assistant, and neither of us ever have to get involved in the conversation. Silliness, I know. So anyway, that is probably one of the best examples of a voice-based conversational system, in the natural language understanding arena. But please understand, it's not a general solution to natural language understanding. It's in a very, very, very narrow domain, a very narrow topic. But in those narrow topics, we're starting to get pretty good. So the secret is, like back in the expert system days, where people had to find economically viable applications for a limited technology. Well, it's the same sort of thing here. You can build a system like that for a very narrow area, It's just, finding the right narrow areas that'll pay you a good dividend. So the next thing I want to talk about is related to natural language understanding. But again, it's not a real solution to natural language. It's not a general solution because we don't have any general solutions to natural language understanding. But what I want to talk about next is something called GPT-3, Generative Pre-trained Transformer 3. 3 because it's the third generation. There was a GPT and then a GPT-2, and now we're up to GPT-3. Now, what is GPT-3? Well, it's a product, it's a system that has been developed by OpenAI. What is OpenAI? Well, Elon Musk, the guy who invented Tesla and the guy who started, well, he didn't invent Tesla. Tesla was actually a company. He bought it in the very early days and remade it in his image. But Tesla actually existed before Musk. But Tesla, Solar City, which is now part of Tesla's Tesla Energy, SpaceX, these are all Elon Musk companies. And Elon Musk companies, the Boring Company, because they drill, they bore, they're into tunnels. But all of Elon Musk companies tend to be very cutting edge and take on really big problems. Well, Musk and one other guy, I've forgotten his name, funded OpenAI. I think they put $1 billion into it to get it started. And basically, Musk is very nervous about artificial general intelligence being created, and he's afraid that if it's created by a Facebook or a Google or a Chinese WeChat or something like that, that would be really, really bad. Because those companies, most of them make their money by monetizing stuff that they know about you. And that's just a really kind of scary proposition from his point of view. So he started OpenAI because he believes that it would be much better if the people focused on generating an AGI, if that code were open source, or if not open source, available to everyone equally. And so that's kind of the idea behind the OpenAI company. So again, what is GPT-3? Well, it was released in this past May. So when it was first announced, it was in May, and I think in June or July, they first started making the API available to people. So you can use the API to form queries that go up to the cloud and use the GPT-3 system to produce results. GPT-3 is a model, a language model that has, I want to say like 175 million parameters that can be tweaked individually. I think it's 175 million. It was in my notes, but I seem to have dropped it somewhere. And it took 36,400 petaflop per second days to train. So think about a computer that's a petaflop per second. Okay, so it's doing 1 petaflop per second, and it's doing that for 36,400 days. That's how long it took to train GPT-3. GPT-3 is bigger than any other program that's ever been attempted like this before. It is 10 times bigger. It has 10 times as many parameters as Microsoft's Turing Natural Language Generator, which a few months ago was the biggest on the planet. So I told you that there are breakthroughs that seem like they happen every few months. I still haven't told you what GPT-3 is. Well, it's kind of hard to put into words. It's not technically a natural language understanding system. What it is a system where it takes in a typed input. It doesn't have a voice interface, or so you can't speak to it, and it can't speak back. Of course, adding those technologies would be trivial. But it takes in typed text, and it produces typed text where the output text is related to the input text. You might say, Mike, that is horribly vague. What do you mean that it's related to the input text? Well, it depends on what you want to do with it. So what are some of the kinds of things that GPT-3 can do? Okay. You can say something like, write me a JavaScript program that implements a web page with the Google logo centered and a Google search box beneath it. And it'll generate the code for that you can run, and you'll have a web page that does that. It can write news articles based on a description of the subject of the article. Write me a news article that claims to have proof of room temperature superconductivity. There isn't such a thing. Back 20, 30 years ago, people thought that there might be room temperature superconductivity, but that all went fizzle. All right, but if you give it a prompt like that, it can generate a news article. It can take a technical paper and produce an easy-to-read summary of that paper. So you might say, summarize the following paper so that a second grader could understand it, and it'll do that. It can answer questions, kind of like a search engine. It can translate between human languages. It can generate quizzes and exams. So these are the types of things that it can do. Now you may be saying, well, but we have programs that do all of these things. And I would say, yes, you are correct. We do have computer programs that can do all of those things. Individual computer programs that humans have programmed or individually trained that can do those individual tasks. GPT-3 can do all of those tasks. So it's far more general purpose than anything that we've built before or that humans have built before. So let me give an example. Now, the internet is awash with videos talking about GPT-3. Every blogger on the planet or vlogger on the planet pretty much that's interested in computing has one of these up. And I didn't really take a long time trying to find the best one. I just tried to find one that was reasonable. So I'm not going to play this whole video. It's 10 minutes long. I'll play the first few minutes of it. But this will give you an idea of what GPT-3 is and what it can do. He goes over some examples. So let's see.
So last week, GPT-3 was released by OpenAI, and it is nothing short but amazing and groundbreaking.
Don't believe the hype.
The largest leap in artificial intelligence that I've seen, and it is able to produce poetry, text, answer questions, do translation, do design, code.
It is a leap in terms of artificial intelligence.
Yeah, don't
in this video, I'm
understand.
going to give you a demo of some of the technologies and some of the things that GPT-3 is able to do, and some of the demos circulating the internet in just the first few days, and how this technology works and what it means for the future of technology, software, and how we use the internet going forward. So GPT-3 comes from a company called OpenAI. So OpenAI was founded by Elon Musk and Sam Altman. Elon Musk is a prolific entrepreneur. You may be familiar with him from SpaceX and Tesla. And Sam Altman was one of the founders of Y Combinator, a very famous startup accelerator. Combined, they invested over $1 billion in OpenAI to advance the state-of-the-art of artificial intelligence and make sure that artificial intelligence was being used for the betterment of mankind. So let's jump in and take a look at what the tech can do. So the first example is an application called Figma, and the developer has built a plugin to Figma that allows users to enter a description of what they want for an application. So in this example, a user is describing an application with a feed and some icons and a user interface. And when he hits submit, the application actually generates an application that looks very much like Instagram. It has all of the buttons, all of the UI, and a scrolling feed. Just astounding in terms of what it's able to do. The next example is a coding example, and so this is dbuild.co, and they're describing an application that is a basic to-do list application. And so what the software is doing is generating a React application, all of the functions and procedures, all of the things that are necessary to create a React component to handle to-do. And you can see it works. You can add items to the to-do list. There's all the events and triggers for handling the interactions of the application, and it's all generated on the fly by artificial intelligence. Just amazing what we're able to do with AI, both design and development aspects. The next example is in Excel. And so we have a table with headers of company, ticker, and year founded. And we ask OpenAI to complete the table, and it's able to fill in the entire table with the data that it thinks we want. Again, it's pulling this information from its corpus of artificial intelligence, and it's trying to be predictive in terms of what it thinks we want in the table. If we don't agree or we want to train it a little bit differently, we can queue it with different elements that start in the table. So here, I actually want the table to be filled in starting from the newest to the oldest. And so I put Twitter and Facebook and then ask it to predict the table. And it's able to understand what I'm trying to do. And again, goes top to bottom all the way in, filling in the year founded information with all the company information. So this example is within Wikipedia. So if you've ever seen a long article, you can't really understand or find the information that you need, and simply have a plugin where you ask the exact question that you want. So in this example, I'm asking, why is bread fluffy? And it's searching the data and information in that article and generating an answer to my question and giving me a citation and location that I can jump to. So really summarizing the data, making it really easy for me to find exactly what I want from large volumes of text and information that are presented.
So I'll stop it there. You're, like I said, the internet is awash with these videos. You know, GPT-3 is the hottest thing since sliced bread in AI right now. I see some people, we're automating ourselves out of our own jobs. Clark's iPhone, that is something that you should watch carefully. We've always argued, well, people who've thought about this have argued that AI is kind of a rising tide, and really technology in general is kind of a rising tide, and that there's like a mountain, and as the water rises, it's getting closer and closer to the peak. Actually, they're kind of it's Twin Peaks, if any of you ever watched that wonderful old show, Twin Peaks. And the reason why they're Twin Peaks, my hands keep vanishing, the reason why they're Twin Peaks is one peak deals with complex, intellectually challenging, and creative work that humans do, like being a college professor, hopefully. And the other peak is manual labor. jobs that require dexterity. So, you know, hairdressers, people who work in fast food, right? Because right now, we can't build a robot that's as flexible as a human being. So you can build a machine that makes burgers, but it's not nearly as flexible. So like when McDonald's adds a new, you know, a new item to the menu, well, that would completely screw up the works. So there are these twin peaks. There are the jobs that are very creative and intellectual, and there are the jobs that are very manual. But the water of technology keeps rising. Now, I've always personally thought that I haven't tried the spicy McNuggets yet. They do sound good though, don't they? The problem, well, from my point of view, I've always thought programmers, developers, academics, we will be the last people. The floodwaters will have risen, and we're going to be at the very tippy top of that mountain. So when we drown, at least we'll be the last to drown. Everybody else will have their jobs will have perished long ago. But you see something like GPT-3, and you start thinking low-level programming tasks might fall relatively quickly to systems like that. I don't know if I should believe you, Zach, or not after the spicy nuggets comment, but in chat he is saying that Microsoft teams up with OpenAI to exclusively license GPT-3 language model. This just came out a couple of hours ago. It's on the Microsoft blog. Can someone verify that? Because you know we live in an age of fake news, and so I'm not questioning your integrity, Zach, but I'm questioning your integrity. I would like to know that that's not fake news. Always verify. Even anything I tell you, verify it. Okay. No, it's real. Okay. And that's what people are saying out there. That's kind of scary. That's actually kind of scary. But you guys are making a point for me, and that is that GPT-3 is currently the hottest thing in AI. Everybody is talking about it. So, you know, a lot of you guys, you know, I've had some people say that they love this first part of the class, and I've had other people say to me in the evaluations, you know, Mike, I'd rather learn about algorithms, and you know, but you know, and I respect that. Some people are just not so squishy-feely, but I would argue that, you know, thinking about the impact of technology and where this stuff could go is critically important. I mean, you don't want to be blindsided by it. And so, you know, I really think you need to keep your eye out on what's going on. You know, this material clearly wasn't in last year's lecture about AI. I'm continuously updating my notes because there's continuously new things that are coming out that are important. When I first started reading about GPT-3, I went, oh, that's interesting. It can write news summaries, and then I read, and it can program, and I went, what? You know, suddenly it caught my attention a lot more when I read that. So be very aware of GPT-3, but don't believe the hype, right? Don't believe the hype. It has real limitations. It has real limitations, and it gets things wrong. I see somebody here in Texas, computers are dumb. AI in its current state has been compared to savants, right? Instead of human savants, computer savants. And what's a savant? A savant is a person, the meaning of the word has changed over the years, but savant currently means someone who is super brilliant in some tiny little area, but in general has reduced mental capacity compared to a typical average person. So Rain Man is an old movie. That's an example of that. Some of these, some savants, for example, can tell you, you give them a date in the past or in the future, and they can tell you the day of the week that is. Oh, that was a Monday, right? And if you go back and you check, they're right. But yet they may be, you know, in other areas, you know, mentally very, very compromised. You know, maybe they can't, you know, add 2 and 3 together. You know, or sometimes there are musical savants, people who are brilliant at hearing a tune and playing it precisely on a computer or composing music, and yet they can't, you know, they can't read, for example. So that's, some people have compared the AI systems that we have today to computer versions of savants. They are very, very, very good in very, very narrow areas. Those areas are getting broader with time, but still they have limitations. So what kind of limitations do they have? Well, I thought this was fun. I ran across it last night. A couple of months back when GPT-3 was released, there was a white paper that was released on arXiv by the scientists, the developers of GPT-3 that described the capabilities of GPT-3. Now, one of the things that I pointed out was that one of the things that GPT-3 can do is it can summarize articles in a getting rid of the technical information as much as possible and sort of translating it into the level of that a child could understand. So I ran across an article on the internet where it's actually become a popular thing to do, which is to take the article that the scientists wrote about GPT-3, feed that article into GPT-3 and ask it to summarize the article so that a layman can understand what's going on. So I thought that it would be fun to excerpt the part of the article that deals with the limitations of GPT-3. So this is GPT-3 in its own words describing its limitations. Technically what's happening is this is GPT-3 summarizing in a easy to read form the technical paper written by the scientists that wrote GPT-3. So here's what it has to say. Don't forget, it's just a writing bot. Finally, it only reads and writes. It does not see or interact. It hasn't ever seen the world. It can do code and language, and that's about it. Now, again, I'm reading you the output of GPT-3 here. Even if a few-shot system is able to learn what humans can do, we can't be sure that it has. It has no world knowledge, no common sense. It does not know about objects. It does not know how to walk downstairs or how things work. And it cannot demonstrate any ability for doing anything else but reading and guessing the answers. Finally, its decisions are not easily interpretable, and sometimes its guesses are way off the mark. We don't really understand why it's making certain decisions. We don't know how to explain them in plain language or make predictions about them in novel situations. It's also not terribly good at prediction outside of data sets it's actually read. So, for example, if you are trying to write a virtual assistant who must answer questions like, quote, if I put cheese in the fridge, will it melt, end quote, GPT-3 probably won't help you. And then there's a parenthetical expression here. I think this was written by the author of the article. who put this together. It says parenthetically, this example may be inspired by Harry Potter and the Sorcerer's Stone, where there's an incident with some pudding. I don't think that that was written by GPT-3. I think that was written by the human who was summarizing this. Anyway, finishing off, regardless of whether this approach works in practice, it is clear that far from having reached the limits of what can be achieved with language modeling, there remains plenty of room for improvement. That said, it did write this article, so not bad, right? So that's the update. GPT-2 has been updated to GPT-3 by feeding it lots more stuff. GPT-3 is used for showing us how smart computers can be by helping us do things on the computer. With GPT-3, computers can now tell us what people say, help us see the meaning of what we say and do, and help describe what we write next in games or stories. We want to use these skills to help everyone understand the world better. So that's GPT-3 summarizing what GPT-3 can't do. I thought that was pretty fun. So let's see if there are any comments here. I'm in this article and I don't like it. Okay, so what can computers do and what can they not do? Hold on. So it seems like there's so many things that computers can do well that maybe it's hard to tell if you're talking to a computer what it can't do. But actually there are some very simple little tests that you can do. Pretty much no system can handle Winograd sentences or Winograd schemas. Remember Terry Winograd, the guy with the really big fuzzy hair from the documentary that I showed last time, who wrote Sherdlu? He wrote Sherdlu, the little Blocks World program that you could talk to by typing out text. Well, Winograd is a very famous computer scientist, and he's come up with, well, there's a whole grouping of sentences called Winograd sentences or Winograd schema that that are very simple and easy to understand, but that show the limitations of computing systems. Generally, computer systems have no common sense, okay? So they don't know anything about the world, just like GPT-3 was saying in that summary. Here's an example sentence. If I were to say to you, the cat tried to squeeze into the box, but it was too big. What does it refer to? The cat tried to squeeze into the box, but it was too big. Everybody, all at once in chat. What does the it stand for? Cat tried to squeeze into the box, but it was too big. Well, everybody knows it's the cat. Now, what if I were to say the cat tried to squeeze into the box, but it was too small? What does the it mean? The cat tried to squeeze into the box, but it was too small. The box. Everybody knows it's the box. But if you look at those two sentences, the only thing I changed was the very last word. One is big and one is small. Syntactically, the sentences, they have exactly the same form, right? So how do you know that the first it is the cat and the second it is the box? Well, the only reason you know that is because you know a lot of stuff about the real world. You know about boxes, and you know about cats, and you know that cats like to climb into boxes, and sometimes it's a tight fit, and if the cat's too big, it's not going to get into the box. It's not going to be able to physically get in the box because You understand cat box physics, right? And because you understand cat box physics, you can understand the meaning of those sentences and you can disambiguate it trivially. Any child, I could read this to a 5-year-old and they would know what the it meant in both cases, right? Yeah, you can quote me on cat box physics. So we're far from from understanding natural language, and the big problem is common sense reason or understanding. So let's see. I've got a video here if I can find it. Show me the video. Let's see. Show me my video. Sorry guys, I have most of these lined up. This one seems to have escaped me. Okay, and I've got to speed this along here, 1745. You may wonder where all of these old videos are coming from. I've actually got in the resource file the entire hour-long documentary. It was from the 1990s called The Machine That Changed the World. An excellent video. Let's see, this is going to 1830.
Was vastly more complex than solving calculus problems.
Even if you take a simple everyday sentence like, Mary saw the bicycle in the store window, she wanted it. It might refer to the bicycle, store window, store, and which it refers to depends not so much on English as on your knowledge of what people want and don't want. If I said, she saw the bicycle through the store window, she looked at it longingly and pressed her nose up against it. That second it probably refers to the store window and not the bicycle. And now you have to bring in knowledge of human anatomy and the fact that people emotionally like to be near things that they want, even if they can't have them, and so forth.
So that's, the guy speaking there, his name is Doug Lennox. Doug has been working on the common sense natural language understanding problem, God, for essentially forever, since the 1980s. Believe it or not, that's dedication. When you dedicate your entire life to one project, essentially. So Doug Lennox believes that you need that computers need common sense to be able to solve the natural language understanding problem. And not only does he believe that, he's been working for, 35 years on the problem. There were, in the early days, there was a lot of excitement that he would break through. Now, he's kind of considered, a backwater, that's using old-fashioned techniques to try to solve difficult problems. But I would be very careful before I render judgment on him to remember that Hinton, the scientist that spent his entire career working on neural networks, was basically ignored and laughed at for decades. Maybe not laughed at, but ignored, and people kind of thought that, yeah, he's working on this area, but he's never going to have any success. And then in the last 10 or 12 years, that approach has completely changed the world. So you know, be careful in the way you judge someone, because you never really know what's going to happen in the end. I want to play you a little more of this documentary, about 3 or 4 minutes of it, that go through Doug Lenat and his approach, and it begins with the problem that shows that that a computer cannot understand simple kind of stories like a little kid could understand. So here we go.
Language researchers were hard at work trying to get computers to follow simple stories as children do. They discovered the problem wasn't what the story said, but it was the huge number of things it left unsaid because they were too obvious to be worth saying. Typical of the kinds of stories which researchers tackled in the early 1970s was this one.
It was Jack's birthday. Jane and Janet were going to Jack's. Let's give him a kite, said Jane. No, he already has one, said Janet. He'll make you take it back.
Could the computer understand the story and answer questions on its meaning? Although it seems easy, it presupposes a vast amount of knowledge. We assume they are going to a birthday party, but it doesn't actually say that.
You notice in that story, it's not clear that they're going to a birthday party. It's just they would give a Jack and they were going to Jack's. It isn't clear why they were buying a kite. It doesn't say anything about birthday presents, and it doesn't say that you bring birthday presents, and it doesn't say the kite was a birthday present. But they thought they had an answer to that. The answer was supposed to be build it into a birthday party frame. The thing after Micro World, which looked promising, was scripts and frames. Then the idea was there is a stereotypical birthday party, and the child has a birthday, then the child has a party, and then people come to the party and they bring gifts and so forth. So even though the story doesn't mention kites, the computer would fill in presents and kites.
Since we judge words by their context, why not give the computer a context by building frames or scripts for the situations it might need? A birthday party frame would contain all the things which usually happen at birthday parties. Once the computer had identified the frame, it could fill in the missing knowledge. But things were not to be so straightforward.
See, this is very similar to the knowledge graph I was talking about that Google uses.
The idea that he already has one, he'll make you take it back. The challenge was, and I think it's unanswered to this day, here's a new bit of information. The information that, in our culture, sadly, children learn, if you get a new one, just like the old one, you have to take the new one back, not the old one. And the question for them was, where are we going to store that information? It doesn't belong in the birthday party frame. It doesn't belong in the department store frame. It's general background knowledge, the horrible thing, general background knowledge reared its head. And then when I learned it, as I usually did, I saw worse things. It occurred to me that the principle, if you have one, you don't want another one just like it, is not much of a strict rule. It doesn't apply to dollar bills. It probably doesn't apply to marbles or cookies. So the principle has got to be something like, well, everything else being equal, if you got one, you don't want another one just like it. But, of course, in the everything else being equal is the whole common sense knowledge problem again, because what is everything else, and how equal does it have to be? I mean, if it's a cookie is that big, maybe one is enough. But then if you're a cookie monster, probably one isn't enough. And all of the knowledge we have about cookies and appetites and cookie monsters and so forth comes in to understand just a simple birthday party story. And so that looked bad.
So that was Hubert Dreyfuss there. He's a guy that's been sort of a critic of AI for decades and decades. But that's a pretty good summary of the problem. There's no, how do you do natural language understanding when you don't really have understanding? So that's a big problem. Anyway, I see that we're pretty much out of time. What we're going to do next time is we're going to cover the last two areas, computer vision and autonomous vehicles. And then we're going to turn our attention to the last chapter of the book I wrote, which is the past, present, and future of computing. We're going to look at the future of computing, and we're going to look at some things that people thought would apply to our time. So in other words, past predictions about what computing would be like today. And then I'm going to talk about some technologies that are out there and how they're developing to give you an idea of where things might be in the next, 20, 30, 40 years. And I'll make a few predictions myself. And that'll be Thursday's lecture. So I think that's about it for today. If anyone has comments, I'll be happy to stay after class and answer any questions you might have. Until then, guys, it was fun. Take care, and I'll see you on Thursday. Bye-bye.